everybody, this is Mrs. Anderson, and we are starting off our year. We are working in Master Math Mentor Notes. They are amazing notes. I love them. And our first unit we're doing is Section 3, Average and Instantaneous Rates of Change. You'll see that some of my stuff will already be filled in for time. Maybe I'll skip ahead every once in a while, so please make sure you are listening to the whole video so you are understanding what's going on. So we're going to start with some diagrams right at the top, and this is really just a reminder that when we have secant lines, this is going to be called the average rate of change. Okay? So remember that secant lines go through 2 points. Then we have our tangent lines. And the tangent line only goes through 1 point. So that tangent line is going to be called the instantaneous rate of change. And as we draw, okay, P to Q, our secant line, as we move Q closer and closer and closer and closer and closer and closer and closer in, we notice that our secant line starts matching up with our tangent line. And that's kind of what we're investigating, is that move in and that difference between the P and Q being very, very small. Okay? So notice that for our naming in here, we're going to have some things. We have the slope of the secant line is M and then an SEC. And the tangent line will be M and then tan. And we always want to recognize that and write that for naming so that we keep track of everything. And we're going to look at f of x equals x squared. So I'm going to take my calculator, and hopefully you have something like this because we want to be practicing those calculator skills. You do get one on our AP test. We're going to turn it on. And just a nice thing every once in a while we want to do is we're going to hit home. We're going to hit 2 for my documents, menu, C. We're going to hit OK. And we're going to clear out all the folders. So it just gives you a nice start. Settings. And we're going to do document settings. I always like to be on float 12 to have as much accuracy as I can. And in this class, we will always be in radians. Calculus is always in radians. Remember, you'd never know who used the calculator before you, so double check that before you start. Make a default, hit OK, and off we go. So I'm going to go into my graph, and I'm still learning how to use this. I'm not always super quick with it, so be patient. I'm going to type in x squared, and we should know that that's a quadratic, forms a parabola, concave up. And then I'm going to go to the table, and I notice that at x is 1, I have a y of 1, and x is 2, a y is 4. And in this beginning here, that's what they're asking us to do. So what I'm going to do over here is just on the side, I'm going to make a little table. So here's my x and here's my y, 0, 0, 1, 1, 2, 4, and 3, 9. And we don't go up to 3, we're really just staying between 2 and 1. So it says, well, when I plug in the value of 2, what did I get? Well, I got 4. So the rise from the point before it. So how far did I go up? Well, I went up 3. And how far did I move over? I moved over 1. So rise over run means my slope is 3. Now I'm going to go to 1.5. And if I put that in the calculator, I'm not very good with switching my tables around. So I'm just going to go back out, and I'm going to square that. And I'm going to find that that's 2.25. Now remember, that's going to be over here somewhere, right? So that's where that guy is. So the rise is from 1. Okay, so this is 2.25 to 1. Becomes 1.25, and the difference between these is 0.25, or sorry, 0.5. 1 minus 1.5. Now I put this in the calculator, and I'm going to get 2.5. Now I filled in the rest of the table. I would pause it at this time and fill it in. You can practice it on your own. Just make sure you understand where the numbers are coming from. All right, so now we get to the next question. Why can't we use this to find the slope of the tangent line at x equals 1? Well, if we're at 1, then the run is 0 because I'm right at 1. Okay, so I'm going to write division by 0. Secant lines. How many points does a secant line use? Hopefully I've already remembered this from my geometry class, but it's 2, or I can look right up above on diagram 1. How many points does a tangent line use? 1. So using the fact that x gets closer to 1, the slope of the secant line approaches the slope of the tangent line. So what is your best guess for the slope of the tangent line? Okay, so as I'm getting closer and closer and closer, right, I'm going to let you guess a second. So at x equals 1, my slope ends up being 2 because it is approaching as I'm going from 1, okay, it keeps getting closer and closer and closer, and it's going to become 2. And I'm looking right here before I get to the 1 where I have the decimals. So let's use an analogy, so a story. You leave at home at 10 a.m. on a trip and arrive at 12. The trip is 100 miles. How fast are you going at 11 a.m.? Well, I mean, do I really know? At 11 a.m. I may have stopped for Bucky's break. So, I don't know. It's unknown. We cannot find the velocity at 11 a.m. because it's called the instantaneous velocity. But we could find the average between the two. So at 11 I don't know, but over the whole trip I could guess. So my total distance is 100 miles. And the time I traveled was 2 hours. And so I have 50 miles per hour. Now I'm going to turn this over to the back, and we're going to have again another table that they've done with this. And they go through again all these different things. So they filled in a bunch of time. So I remember I started at 10 and I'm going to 12. Okay? So, and over here I'm really comparing between 11:30 to 11. So how long was I going? I was going a half an hour, a quarter of an hour, a sixth of an hour, a 12th of an hour, a 60th. Think about that. There's 60 minutes in an hour. Okay, half of that becomes again 1 over 120, and then 1 over 3,600. My average velocity, so that's going to be distance divided by time. Remember, when I take a fraction and I divide by that fraction, I'm multiplying by the reciprocal. So this becomes 24 times 2, which is 48 miles per hour. So I have 52, 60, 66, 48, 60, 54.5, and I don't know because now I'm dividing by 0. I traveled 0 and I have 0. That does not make that 0. That's not possible. So do I really know the instantaneous velocity at 11 a.m.? Okay, so let's talk about it. Why can't we use this technique to find the instantaneous velocity at 11 a.m.? So again, we're dividing by 0. Average velocity uses how many times? Think back to diagram 1. Average velocity, 2 points. Instantaneous, 1 point. That's going to be very important that you can tell the difference between average and instantaneous. Those are key vocabulary words. As the time duration after 11 becomes small, the instantaneous velocity 11 a.m. is much more likely to be very close to which of these values? So again, we're going to do 54.5 miles per hour because it is the tiniest bit past 11. So as good as we can get, we could assume that that is going to be the same at that instantaneous. And so the answer here is actually going to be almost no time variation. So we're going to take 2 points and give them general conditions. And you're going to notice that, hey, this is starting to look like geometry. I know we don't want to revisit it, but we may need to. So again, here's a curve, our function f of x. We have our 2 points. So right here, let us take these 2 points and give them general conditions. So we're going to draw the right triangle below, okay? And notice, to do this becomes our hypotenuse, okay? And so we just have our rise over run, y1 minus y0. Remember, this is going to be our first point, and this is called our initial point, okay? And in our calculus world, we're going to be calling this f of x. So f of x means y value. Okay, so it's just a translation. Concentrating on the tangent line at point P. We've shown the above formula does not work. So remember, here's our tangent line at point P. Why not? So again, there we go. Why not? Because again, we're dividing by 0. Because that little bit right next to it is so tiny. Since h, and that's the move from the initial point just a little bit, ends up being, so h is that horizontal distance, that little small increment we're moving next to. Okay? It can be written as these 2 ways. So, since the secant is this, it can also follow that the value is x of naught plus h minus f x of naught over h. And this is going to become what we use for quite a while. This is a really important slope formula. The important step, we showed that the tangent line P is defined as the secant line between P and Q. Q gets closer to P. As Q gets closer to P, x1 is becoming x naught. So that difference is so small. The horizontal distance between P and Q gets close to 0. So we have the starting point for differential calculus. And this is our big formula. We want to highlight it. We want to star it. We want to bubble it. It is going to come back again and again and again. Okay? Note that h cannot actually be equal to 0. And again, if that happens, we're going to be dividing by 0. So we're going to make this as small as possible, and that could be tons and tons and tons of zeros and a 1. That's not 0. Most of the time we would say it is, but that's actually not 0 with that 1 on the end. So we're going to have that kind of incremental change between the first point to the next point. Okay, let's look at the last thing. These are our 3 formulas you need to know. So what do we want to do with them? Maybe we want to box them. Maybe we want to highlight them. I don't even know that I have any good markers right now. But I'm going to do these in green. And I like green because I'm going to call these my money formulas. If I learn these formulas and I pass my AP test, then I'm going to go to college with credits. I'm going to save money for my calculus class, and that means I'm going to be a step ahead and understand better for my next calculus class. So I'm saving money, but I'll be making money with a better career. Okay? So average rate of change is just our general slope. Instantaneous, We kind of have this big boy and girl formula we want to know. It gets infinitely close to 0. And remember, we always have our point-slope equation, which was from Algebra 1 and geometry. All right, with that, we're going to try a couple of classwork problems before you jump into homework. Best of luck!